Okay, so as we look at these two questions, suppose you lift an object with decreasing speed. Compare the force it exerts, the force you exert on the object to the gravitational force on the object, and compare the force you exert on the object to the force it exerts on you. Okay, so let's take a look at this guy. Is what we have, oh, wrong side. What we have is we have my hand right here, right, holding this object up. And I'm exerting a force on the object, and that's the normal force, upward, right? And there's a force of gravity pulling downward on it, right? And so the first thing we ask ourselves is, how are they related? Are they always equal and opposite? This goes back right to here. Compare the force you exert on the object to the force it exerts on you. There's a normal force pushing down on my hand, right? And that's the repulsive force between these two objects. And so this goes back to Newton's law, which isn't for every force there's an equal and opposite force. It says, given a force, there is a reaction, there's an action and a reaction. So for a single force, for this normal force, so the normal force of Pete's hand on the object, it's equal to the negative of the normal force of the object on the hand. Okay, those are your equal and opposite forces. Okay, so let's erase this one for now, because that is on the hand. And let's just look at the forces on the object. Okay, so we've solved the second one already, B. But compare the force you exert on the object to the gravitational force on the object. And we recognize these are not equal and opposite pairs like these are here. Okay, these are two different forces acting on the same object, and they can be controlled differently. What we know is the vector sum of the forces is equal to mass times acceleration. Okay, so if these are equal and opposite, which they could be, that means the vector sum of the forces would be equal to 0. The force of gravity plus a normal force would equal 0, and the acceleration would be 0. If the acceleration is upward, then the normal force is going to be greater than the gravitational force in order to give you that force upward, to accelerate it upward. And if the force of gravity is greater than the normal force, then the acceleration will be downward. Okay, certainly if you pull your hand out from under it and the normal force goes to 0, this force is greater and it accelerates down. We know that. So let's take a look. What happens? You are lifting it with decreasing speed. What does that mean? That means one moment it's going up very fast. V0 is equal to, let's say, 10 meters per second. And then a moment later, what's up here, V final is equal to 2 meters per second. Okay, and I should make this velocity vector look a little more realistic. Okay, so we know if it continued at 10 meters per second, then the acceleration would be 0. That's not the case. If it got bigger, if it was 12 meters per second later, then the acceleration would be upwards. I'm increasing it, right? That's not the case. The velocity is getting smaller and smaller, so the acceleration is actually downwards. And so we recognize because acceleration is downwards, the net force is downwards, and that means gravity must be greater than the normal force. So the force of gravity in this case, because I'm moving up but I'm slowing down, the force of gravity must be greater than the normal force. Okay, and we could look at it this way. We know that V final is equal to V0 plus delta V, right? And so here we would have our 10 meters per second is the V0, right? So V0 plus delta V. Here's delta V minus 8 meters per second, right? When you add those two together, V final plus delta V is equal to, V0 plus delta V is equal to V final. Okay. So let's take a look at the next one. is it possible to have constant speed and acceleration not equal to 0? Let's see. Here we have constant speed. We're always moving at the same speed. And we can see, oh, acceleration is equal to the change in velocity over change in time. Okay? So there's no change in velocity here. So we might conclude that, oh, right, if the speed is the same, then the acceleration is always 0. And they're asking us, can it be non-zero? Oh yes, what if we have v naught here and v final here? Right, then what you have is you have a change in velocity, but the speed is the same. Right? Or if you go in a circle, right, your velocity is changing, you're getting acceleration, centripetal acceleration into the center, but the speed is the same. In this case, v naught and v final, this is how I write it, because we recognize v final is equal to v naught plus delta v. Right? So v final, v naught plus delta v. Right? So even though you had the same speeds, you had a change in velocity, which comes with an acceleration. Right? What we know is that acceleration equals change in velocity over change in time. So change in velocity is acceleration times change in time. V final is equal to v naught plus acceleration times time. Last one. Is it possible to run at high speed and have an average velocity of 0? Certainly it is, right? We know that average velocity is just your change in displacement. Your change in displacement over change in time. Right? How fast you're changing your displacement. So any way that you could run such that your change in displacement is 0, you just have to end up where you start. So you could start at one point, zing, and then move back and be at the same place. That would have an average velocity of 0. You could go in a circle, right? And you'd have a velocity like this plus this. If you average those together, you'd get 0. But you can also see you come back to the same place, delta x equals 0. And so your average velocity is going to be 0.